Okay, thanks for the great introduction. Hello, everyone, and welcome to the Siemens User-to-User Conference today in Munich. I'm excited to present on behalf of my colleagues and myself a presentation titled ATPG-based Die-to-Die Interconnect Fault Coverage in 3D Stacked IC using Tessent Test Solutions. I'm presenting both Anhalt University of Applied Science and also Racyics, and I'm happy to have our contributors and co-author of this presentation, which are also present in this conference, Thilo Wagner, our colleagues from Racyics, and also Ralf Sommer from Siemens colleague. We have also Professor Dr. Ingo Schmelski from University of Applied Science, who contributed in this research and also industrial research. And I would like to also acknowledge the contribution of Martin Naim and also Andreas Watz, who really contributed to achieve a good solution for die-to-die interconnect testing. Okay. Not working.
So where's the first slide?
Okay.
You have to do it hard way. Yeah, there we go.
Okay, allow me to introduce Racyics. Racyics is the leading ASIC and SoC design partner in Germany. We are located, the headquarters is in Dresden. Our main DFT team, majority of the DFT team are based in Frankfurt, and we are also having a team in Duisburg. So our partnership with ARM and Global Foundry strengthen us to deliver a high-quality design services for the customers. Lee also already introduced me, so we will move to the technical presentation of today. So we will start with an overview of heterogeneous integration. So in heterogeneous integration, for example, in a system in package, we bring all the components together and we stack them either side by side or vertical stacking together. For example, CPU, I/O, GPU, memories, also some MEMS, oscillators, and also some filters together to make a system. And the reason behind this is that we already seen an example of the big SoC in Lee's presentation. It was from Apple's SoC, which had almost 92 billion transistors in one big SoC. And the question is to what extent we are going to shrink the nodes in SoCs, and to what extent are we going to enlarge the size of the die. So this leads us, the industries, to think about the heterogeneous integration and the die disaggregation, it's also called. So using chiplets to bring them all together and make a system will bring lots of benefits. For example, it will reduce the cost because we use smaller dies. It will enhance the yield. We can also optimize the design using the different technology nodes. For example, if you look at this, we need CPU from 5 nanometer from Fab 1. We need GPU from Fab 3 with 7 nanometers, and we don't need a small size of nodes for I/O. We can use, for example, 90 nanometers for I/O. So this brings us capability and flexibility to optimize our design with different nodes. Chiplets can also be reused. Vendors can reuse their chiplets in different designs using the 2.5D and 3D IC packaging. It also overcomes the reticle size limitation from manufacturing side. For example, we enlarge the size of the SoC, so we will reach the limit of the reticle size. So this will be a solution to overcome the reticle size. It will be scalable, of course, because you can integrate multiple chiplets into one package. The most important thing for vendors is it will make a market for them. So for chiplet vendors, it will create a market. So if you look at this example, we only have memory stack, which is vertical, and the other dies are integrated side by side probably in a passive silicon interposer. We can also stack vertical dies, logic on logic dies. So heterogeneous integration enable us and leverage the capability to vertically stack the dies on top of each other, especially logic on logic dies. Logic on logic dies is the forefront of industrial research. So initial products are already being developed. What we see here in this diagram, we are having a base die, die 1, and we are stacking other dies on top of each other. So this is a 3-layer 3D stacked IC, and the connection between these dies will be through the TSVs and also the microbumps. So those will be very, very tiny microbumps to connect multiple dies in each layer. The main concern is the testability. Of course, 3D IC, especially heterogeneous integration, brings lots of benefits, but nothing is for free. Apart from mechanical stress, thermal reliability, testability is a major challenge. And the good thing is that IEEE 1838 already sought this solution to access the 3D ICs through the base die. Already it was released in 2019. However, it leaves some questions unanswered, especially the die-to-die interconnect testing and repair in multi-die devices. So that's why an IEEE group called P3405 is established to append this gap, to standardize the die-to-die interconnect testing and repair. Before going deeper into testability and testing of the die-to-die interconnects, we need to understand what is the die-to-die interconnect. The die-to-die interconnect could be a link between an I/O path from one die directly to another die. So this would be a basic definition of a die-to-die interconnect. Moving forward, if we look at the 3D IC, for example, in this example, we are having three layer of the dies stacked on top of each other, and the interconnects must be tested. So in which level, in which steps, that's very important, and still it's under the debate. But mostly, we want to test each layer at each stage. So in order to find the defects in interconnects. So the defects, especially the shorts and open defects in the interconnects, are the main challenge. We need to detect them before stacking multiple dies in an early stage. So die-to-die interconnect could be tested at a wafer level through the short loop back patterns, or it can be tested at the stack level. So possibly, for example, using the best built-in subtest solution, LFSR-based built-in subtest solution, or we can also use the scan-based ATPG solution or boundary scan. So at which level? Either we can do it at the midpoint level where we stack only one layer. So before stacking another layer, we want to make sure that these interconnects are fault-free. So that's why we need to test in different stages. One is in mid-bond level, and the other is in full bond. So there are lots of solutions to test the interconnects. As I said, the best built-in subtest solution, and also the boundary scan, which is a serial port. But depending on the application, an ATE-based solution will be sufficient to test the die-to-die interconnects. If we look at the defects, before going to defects, if we look at the array, a microbump array of the die-to-die interconnect, it looks something similar to this. And it is arranged in a rectangular shape. So these microbumps, if you see the pitch of these microbumps, it's around 40 to 50 micrometers. And it will reach to 10 micrometers in the near future. the defects, mostly the defects, the statistics says that 95% of the defects will be short among these interconnects, and 5% of the defects will be open. So which means that shorts are 20x more than open defects in die-to-die interconnects. So there could be a weak short like this, and or it could be a hard short like this, completely short between microbumps. And the opens could be some foreign materials to crack to see some crack inside here, and also some misalignment during the stacking. So these are the main physical defects. So now we understand that what are the common defects in die-to-die interconnects. So how we approach to tackle this solution and to find those defects while we are testing. So first we need to do some modeling to convert these physical defects into logical faults. So in order to do this, Tessent has a solution for that to explicitly define the fault model. It's called user-defined fault model, UDFM. So if we consider, for example, a bridging fault, which will be the fault model for the short physical defects, we are having fault-free circuit like this, and if the one of the interconnects dominates the other one, there will be a faulty circuit model. And similarly, if we have some opens like this, so we can detect. How we do this, there is a special syntax for UDFM. It's already well documented in Tessent user manual, how to script this, how to write the fault model for these interconnects, for bridging and open. So Tessent can give us this capability to explicitly define our fault models. But the question is now, okay, we know what are the defects and we know how to model these defects. So now the question is, okay, shall we feed this to ATPG tool to run and to generate patterns? And the answer will be no. Why? Because in a layout agnostic bridge example, if we don't understand the layout information and the position of those interconnects, so there will be too many faults. So for example, here, an interconnect A with interconnect B, logically, there will be no short between these two because they are located very far. But if we don't have the information, we just only model these faults, so this will be the situation. And we will be having n times n minus 1 divided by 2 number of potential bridge faults, which is too many. So what we do is we need the layout information. Interconnects are generally arranged in a rectangular and hexagonal shapes. So rectangular is similar to this. Hexagonal, we are having some offsets. Here we are having, for example, in row number 2 and row number 4, we are having some offsets. So why we are having different array? Because literature says that hexagonal arrays can accommodate 10% more interconnects, 10% more bumps in a same size of array compared to the rectangular shape. So that's why nowadays industries are moving to manufacture hexagonal arrays instead of rectangular, because it can accommodate more interconnect. So how we can identify that, okay, how to model realistically the shorts among the interconnects in these arrays? If you look at the rectangular, for example, we are having an interconnect I23. So we look at the surrounding interconnects and we consider only those interconnects which surrounds this victim interconnects. So for example, maximum number of aggressors per victim in a rectangular shape could be 8, but it depends on the location of the interconnects. For example, here we are having 3 and here we are having 5. So similarly, if we look at the hexagonal shape, we are having more numbers. We are having 12. Why? We could consider only 6, the inner circle, surrounding circle of the interconnects in hexagonal, but to take some safety measures, we consider the outer circle also. So that's why we're having 12 aggressors per victim in a hexagonal shape. So definitely placement information is crucial, and it helps us to reduce the number of patterns generated, and this will lead us also to have less test time. How to actually do this? We have now the physical defects. We know how to model these defects, and we know how to consider the potential aggressors for each victim. So if we look at the interconnect map, it is similar to a real product. We are having an interconnect map. So if we take the information from the place and route tool, we will have similar something like this, a CSV file with the format of XY net. XY is the XY coordinates for the interconnect, and the name of the nets are, for example, die-to-die net 1. So we are extracting the data from place and route tool, and then we need to fault the models in such a way to have a realistic short, specifically the victim with each associated aggressors. So what we do here is we can split these, for example, cluster. We are having a big cluster, for example. We can split this to bundles. Sometimes bundles could have inter-bundle bridges, but most of the times, if we look at the bundles, it will be a little bit far away from each other. So not necessarily, we will not consider the bundle interconnects. In order to do this, one solution is to do it manually. So if we do it manually, for each fault, we need to write at least 10 lines of syntax for UDFM for each interconnect. So think about it, how tedious job this will be. So what we did, we developed an algorithm to automate this process. So we need the UDFM file. Our final file will be the UDFM, the .udfm file, to feed it as a fault universe to the ATPG tool to generate the patterns for these interconnects. But how to do this? We need to automate this, first reading the interconnect coordinates, and then doing some precision and rounding error, handling error, because there will be a long floating point. You will get in trouble if you don't take care of this. And then you need to find the relative unit distance and position of these interconnects in order to find whether this is rectangular or hexagonal. And on the fly, you can map it to a global system of coordinates. So for the purpose of debugging, you can generate some files to read and check for debugging, but not necessarily. The only file we need is the UDFM. And once we have done the mapping, we can generate the aggressors per victim, a file which has each aggressors with associated victim. So we need this UDFM file as a fault universe. So the question will be that how is this scalable or not, this solution? Because in the future, we will be talking about tens of thousands of interconnects. So is it scalable or not? We have tested this. We have tested for 10,000 interconnects. If you look at this graph, we are having 10 by 10 rows and columns, number of rows and columns in an array, starting from 10 up to 100 by 100, which will be 10,000 interconnects. And in the worst case scenario, we need only 10 seconds to generate a realistic fault universe for 10,000 die-to-die interconnects. And is this less or more time compared to other process and EDA tools? Of course, it's very less time just to run the file, feed your input file and run it, and you will get the fault universe in 10 seconds. We also tested, even though the algorithm is written in Tcl script, but we even evaluated this to see how will be the memory usage, because Tickle is a dynamic language. We don't need to see how it allocate the memory, but if we look at this, it's we are in the era of 90s, 5 megabit. Yeah, that's why we say that our solution is scalable. So now we have the information. So we have fault universe. Shall we feed it to the ATPG tool to generate the patterns? Well, if you feed it to ATPG tool, will complain and you will ask us that, okay, how I should access those interconnects. So now the question comes to the test access mechanism. It's already defined and already in the IEEE 1838, we are having the how to access the 3D IC. But if we look at our test case, for example, it's similar. It's the same test case from Tessent. We are having a base die. We are having 4 other dies on top of this base die. We are having some functional core. We wrap those functional cores using the gray box solution of Tessent, and then we also put some P-tap and S-taps to connect these dies. So it's compliant with IEEE standards. And apart from that, the major and important part is the DWR, the die wrapper registers, which serves as a launch and capture point for the functional interconnects. If you look at the functional interconnects, so one die wrapper register will serve as a launch and the other as a capture to test those interconnects. So it's already defined in IEEE 1838, the DWR. We can also leverage the SSN bus to do this in parallel and packetized data and shift and capture. Yeah, Tessent multi-die enhances the time for us, and we can do it. It's already there in Tessent multi-die product. Okay, now we have tested those interconnects in our test case with different scenarios. If we look at this, we had 24 number of scenarios which we tested our die-to-die interconnects. And the test scenario performed for both mid bond stack and full bond stack, for both static test and at speed test, to look at the results of ATPG and test statistic. If you look at this, for example, in a rectangular array, we are having 64 number of interconnects, and in a hexagonal, for example, here we are testing in a full bond with 128 interconnects, so different scenarios. What I will show you as a sample is a full bond stack for the at speed test with 128 interconnects. How does it look when we test? And we will see the ATPG result here. So the test scenario is a full bond, and it is a hexagonal array. We have our fault universe. We feed it to the ATPG tool, and then we generate the pattern. So if we have a bundle size of 16, 32, and 64, similarly, we are having the number of faults for each configuration. So the number of patterns generated for these interconnects are ranged between 29 and 30. And the good thing is that we achieved 100% test coverage, fault coverage, and ATPG effectiveness. And if we look at the tester statistics, we have done this testing with SSN and at 200 megahertz clock frequency. The important thing is that if we look at the test setup and SSN setup, it will be always the same in the same configuration. For example, if we are having a full bond, we are having 3 layers. The test time for test setup and SSN setup will remain the same. The only thing which differ is the shift and capture cycle. The shift and capture cycles definitely depends on the number of patterns. And if we look at the test time, so maximum we will be having around 900 microseconds to test those interconnects. Well, we found some interesting facts of the testing in all scenarios. The first thing is that we understand that hexagonal array configurations will have larger fault universe than rectangular. That's because we are having more number of aggressors per victim in hexagonal array compared to the rectangular array. The second thing is that what we found is we tested and we achieved 100% fault and test coverage in all test scenarios. And regarding the test pattern generation, which we cannot predict, the ATPG tool is the total number of faults does not consistently determine the quantity of the test. We will show you in the next slide how it looks like, because it's not the linear relation. If you have a larger number of interconnects or maybe number of faults, you will get a larger number of test patterns to test them. So that's because the ATPG engine of Tessent might be designed for a much more larger scale. So that's why we cannot predict the linear relationship between these. And we already saw that the consistency of the test and SSN setup times, which remain the same in each configuration. The shift and capture cycles dependency on the number of test patterns. When the number of test patterns grows, also the shift and capture cycles grows. We can see in the next slide the relative impact of the test patterns. So as I described, the number of test patterns has a linear relations with the capture and shift cycles. If we have more number of the test patterns, definitely we will have more shift and capture cycles. For example, the blue line shows the full bond stack and the red line shows mid bond stack. If we have generated only 8 number of patterns for full bond stacks, we will be having around 4,000 cycles shift and capture. But if we generate 31 number of test patterns, we will be having almost 11,000 shift and capture cycles. So important thing is the relative impact of the shift and capture cycles. So the majority of the time will be spent on test and SSN setup in the configuration of the 3D IC. Even if we increase the number of the test patterns, which will be if we are having large number of interconnects, if we look at the total test time, there will be no big differences. That's because the amount of time which will be spent on the shift and capture is much more or less than test setup and SSN setup. So that finally we can say that you can test 128 die-to-die interconnects in a 3-layer or 5-die stack with 900 microseconds if you have 200 megahertz clock frequency. To conclude this, we have seen the complexity and the challenges of die-to-die interconnect testing. How important is this for reliability of the 3D ICs, and how industries are working so hard to tackle these issues. This will be a great achievement if IEEE P3405 release the standards for chiplets die-to-die interconnects, and this will actually enables the vendors to produce their own chiplets and to sell it into the market. And the only thing which vendors are looking at is the standardization of these chiplet interconnect test and repair. And thank you for attention. I'm open for any question. And at the end, I would like to thank again from Siemens for arranging this insightful event. Thank you very much.